Hello, welcome back. We'll be doing a worked out example on related to chapter 17. This is for anchoring into concrete. So we'll take a problem, try to determine the shear capacity of the anchors. Um, as usual, the reason I'm doing these videos are because structural codes are often heavy on text, but light on visuals. If you look at the ACI 318, you'll see a bunch of text, but then very few sketches. So my goal is to take these dense, complex clauses and bridge the gap with simple hand-drawn sketches. I'll not be using any formal presentation, but I'll be doing just chicken scratches on the screen itself, on the code canvas itself, right? Because in an exam setting, you don't have, you only have access to a white paper and the soft copy of the code, right? So we'll be scrolling a bunch of scrolling through a bunch of sections and then doing hand sketches then and there. And the intent is to get used to the uh, different sections of the code and develop a mental image of all the concepts, right? So this visual association makes it easier for you to recall specific requirements when you are in a under pressure in an exam setting. In this video, again, we'll be talking about a problem related to chapter 17, which is anchoring into concrete. So let's get started. So chapter 17, again, we are talking about ACI code here. Chapter 17, this is anchoring into concrete, right? Three main sections. This section here, 17.3, talks about general requirements of strength of anchors, and it has strength reduction factors and all that. And it will also talk about different limit states. We covered all those limit states in the previous video. This video is all about a worked out example. Example looks simple, but there's so much visualization that is needed to, for example, the shear planes. I mean um, the weak planes when shear gets transmitted through the anchors and all that, they have to be visualized for you to be in a position to calculate them easily under an exam setting. To calculate these areas, there are few formulae, but then it is better to get a visual of the areas before you can start plugging and checking numbers. Okay. 17.4, like how I said, is all about the tensile loading, and 17.5 is about shear loading. So we'll be switching this particular example that we are doing. We'll be talking about shear, so we'll be doing this. But then remember, even if it is shear, sometimes you need to bank on the tensile strength to calculate the shear in certain limit states. So we'll be also jumping back and forth between 17.4 and 17.5. 17.6, just interaction. So if you have your tension and you have shear, then how do you know if these two things interact and the final outcome is good? So we need to we need to look at this section to understand how that interaction can be taken care. Okay. Just thumb rules about edge distance, spacing, thickness, and all that. And then this is all about installation and other requirements. Okay, so we'll be jumping straight to what section. Let's go to section. Let's go to the problem description first, and then we'll jump into the section. Okay. So here is the problem description. We have this is the information that is given. We have a column 24 by 24, right? And then I want to get rid of this arrow here. Okay, we have a column 24 by 24. There are cast-in anchors. They are arranged in a certain way. I'll show you the arrangement. The diameter of the cast-in anchors is 3/4. Bolt spacing in one direction is center to center is 5, and other direction is 8. So unequal spacing. Normal weight concrete there. FC prime of the concrete is 3500 psi. The ultimate strength FUTA is 75 ksi, and we are assuming that the concrete is uncracked under service loads, not cracked. There is some reinforcement around the concrete. For example, number 4 tie reinforcement at 4 4 in spacing, but they are not calling We don't have all the details. So yes, there is reinforcement, but we'll assume that there is no supplemental reinforcement in this problem. Okay. Um, the question is to find out the shear strength of the connection in shear. Okay. So here is let's draw this. Okay, that's the 24 by 24 column. Um, um, Slight detail here. There is also a grout like that, and then here is your base plate, and then let's say maybe this is an eye or something. Oops. Okay, and then there is an anchor here. There is an anchor there. Okay, so there are two rows of anchors. In this direction, the spacing is 5 inches. But in the other direction, the spacing is, and here is the pedestal. Sorry, the another information HEF, which is embedment depth of this anchor, is 8 inches. Okay, so the anchor is getting embedded into concrete to a distance of 8 inches. Okay, so that's our setup. Now, if you look at it, let's look at it in the plan view. In the plan view, your column is like that, right? So this is a 24 by 24. Okay, there are 4 bolts like this, 2 rows. This is 1 row, that is another row. This is the row closest to the edge. Let's call this distance. Distance is 5 for the problem description. This is 8 inches per problem description. That is again center to center. The shear being applied is in this direction, and the magnitude of shear is like the applied shear is like 30 kips. Okay, and there is also force being applied in that direction. The ultimate force is like 400 kips. Okay, so that means the shear VU is being applied, being factored shear being applied is 30 kips here. Okay, and for the question we need to qualify. We need to check if this connection, when I say connection, the connection between the column and the footing is good enough, right? So let's go back to the code and see what all limit states we need to consider in shear, and then we'll come back to this canvas here. Okay, so code again. So that is all discussed in chapter in this section here, which is roughly page 231. Let's see, where is 231? Okay, 231 here, right? And if you can see here, this is tension. These three, that is also tension. So we're not interested in that. That is pull out strength and tension. Concrete side face blowout in tension. We are not worried about any of these. Ours is not an adhesive, so we're not going to worry about that. We are worried about steel strength of anchor in shear, concrete breakout strength of anchor in shear, concrete pry-out strength of anchor in shear. So we'll be talking about these three limit states. Okay, so let us calculate this one first, which is the steel strength of anchor in shear. So we need to jump to 17.5.1. Okay, so 17.5.1, we'll have to do a lot of we'll have to go down. That means 17.4 is all about tension, like I said, and once we hit 17.5, we start talking about shear. Okay, so 17.5.1. So this is steel strength of anchor in shear. If you have if this is for a single for cast-in headed stud anchor, right? Ours is a cast-in headed bolt, because remember in the problem statement you have the diameter of the bolt as 3 by 4 inches. So cast-in, but then 3 by 4 inch diameter bolt, right? So ours is a casted head bolt. So we'll be looking at this particular equation here. VSA is 0.6 times ASEV FUTA. Again, ASE means steel effective, and then V signifies the area. Okay, so we're talking about area of that particular thing in shear. and then FUTA is your ultimate strength. That should be less than 1200, sorry, 125, 1230 psi, 125,000 psi. Okay, let's see if there's anything else that needs to be considered. If you go here, you see that there's this section here which says where anchors are used with a built-up grout pad, which is what we have. The nominal strength shall be multiplied by a factor of 0.8. So the nominal strength is the strength that you calculate from here. You multiply this strength by 0.8, right? And that is because code doesn't explain that too well, but then um, here is your this one, and this is where you have a grout, right? And then you have your base plate, then the column, and then the anchors, let's say. So when the load from the column, the shear load from the column comes, the load gets transferred onto this interface here, but the anchors start getting engaged at this location. So there is an additional moment. Let's say this is E, then there is an additional moment that is getting generated on the anchors. Now, when you have moment and shear combination, then then your shear capacity has to be reduced slightly, right? So the code accounts for that fact. What it is saying is, if because of the presence of this grout, you need to account for reduced shear strength, and that is what we are achieving with this 0.8 factor. Okay. So let's transfer that information into our whiteboard, and then we'll go from there. Okay. So we are here. Let's start with the first limit state with this, which is the 17.5.1. That is strength of steel in shear. Okay. Let's talk about strength of steel in shear, and then we'll come back. So strength of steel in shear, as we saw, it is nothing but VSA is 0.6 times the ASEV times the FUTA. But then there is an additional 0.8 factor because we have grout here. Okay. So that is nothing but 0.6. ACV is the effective area of 3x4 diameter bolt. If you look at table, usually it's given in the problem statement, but if you have to find it out from the steel manual table 17.17, and you find out that the effective area for a 3x4 diameter bolt is 0.334 inch square. Okay. So this times 0.334 inch square times our FUTA is 75 KSI times our factor of 0.8. Okay, so that would be the VSA, that is the strength of one nominal strength of one bolt. But if you want the nominal phi VU, sorry, phi VN, so factored nominal strength. So you apply that factor on your nominal strength, correct? So this will be 7.8156 kips. So phi times 7.8156 kips, right? Now to find out the phi factor, so this phi factor is for shear, correct? And this is for the steel and not for the concrete. So if you go back to the code, and go to the strength reduction factors are roughly 235, right? So if you go look here, what you will see here is that there are a bunch of factors. There are factors for shear loads and tension loads. But if the anchor design is governed by strength of ductile steel, then you'll have to pick up information from there. If it is by brittle steel, then you have to pick up information from here, right? If you're talking anchor, if anchor or anchors are governed by concrete breakout, side face blowout, pull out, pry out strength, now you have a condition A and condition B to check, and you will have to pull your information from the appropriate paragraph there, right? So in our case, we are here, right? Um, this is steel, ductile steel, and then we are talking about shear loads. So our strength reduction factor phi is equal to 0.65. Okay, but if we are talking about other limit states of concrete breakout, side face blowout, pull out, pry out, then we'll look into we'll find out if we are in condition A or condition B, and we'll think if we are, we'll see if we are talking about the shear or tension, and then pick up the right value there. Okay. So again, this section is all about your strength reduction factors. So we found out that our strength reduction factor is 0.65. So come back here and then multiply it by. So that value is 0.65 times 7.8156 kips, correct? But then we also have 4 bolts. So from here to here is a capacity of 1 bolt, right? Because you consider the area that you considered is the area of 1 bolt. So you calculate that, multiply with the times 4 to calculate your phi Vn. So the phi Vn value here is equal to, it will come out to 4 times of phi VSA, which is equal to 31.26 kips. Okay, so phi Vn. So that is the capacity of all the 4 bolts. That is how much you need to apply for the steel bolts to shear off, assuming the concrete is strong. Okay, but let's check if the concrete. Um, let's check the other limit states. Okay. Now the second limit state that we are worried about is that we'll be checking is um, the second one would be the concrete breakout. Okay. So when it comes to concrete breakout, I need to draw a sketch here for you. Let's see. So this is our column like that, and we have anchors. We have another anchor here, right? This is looking from the top, and there is a shear. So when you apply shear like this, remember when you have an anchor like that and you apply shear, we talked about this yesterday again or in the previous session. The failure surface looking from the top is going to be this wide. The width of the failure surface is 1.5, and let us say this distance is the CA1 edge distance. In this case, we'll have to find out what our CA1 is, but let's say that is CA1. Then 1.5 CA1 on this side from here to here, and 1.5 CA1 from here to here. So this is 3 CA1. That is the length of our failure surface. Okay. So in the problem description, so let's calculate the CA1, CA2 and see where we stand. So this is 5, this is 24, this is 24, right? So CA1 is nothing but from here to here, correct? So that is this distance CA1 is 24 minus 5 by 2, which is 9.5 inches. Okay. Now in this direction, this spacing is 8. So this is 24, correct? So 24 minus 8 by 2, which is another 8. So 8, 8, 8. So that distance there from here, from this center line to there is called the CA2. Okay. So the edge that we are talking about is this one. The load is in that direction. The distance, so that distance is called CA1 for the code. Okay. So let's write down those values so that we don't We can keep track. CA1 is 9.5 inches. CA2 is equal to 8.0 inches. Embedment depth, which is HEF, is in the problem statement 8 inches. Okay. So when you apply shear like that, we need to consider two load cases. Okay. So case one is you have your pedestal like that, and you're applying shear, right? You're applying shear like this. Now, when you apply shear on this bolt, the width of the failure surface is 1.5 CA1, which is 1.5 times your CA1 is 9.5, which is 14.25. So from here to there is 14.25. This is 8, right? So the failure surface will be something like that. Okay. And same thing in this direction, it will be from this center line to here will be 14.25. Same thing for this surface here, like that, and like this, right? So that is how the failure surface will look. That, and that, right? If you look at the failure, if you look at this pedestal from this view, then you have your these two anchors here, and then the depth of the failure surface is 1.5 CA1, which is 14.25 for the chord, right? And at a 35 degrees angle. So something like that, something like this, right? And if you look at it from this view, now you have two anchors like that, right? But this entire width, the failure surface is cutting the entire width. It is in fact larger than the width, right? So the failure surface, that dotted line, if you extend it, it's going to go like that. So because there's no concrete there, we assume that that is the width of the failure surface, which is this width here, right? And in this direction, that depth is nothing but this depth here. So this is the projected area of failure. Okay, in the code, this is called AVC, projected area of the thing. So if you do a 3D view of this, so it will look like that, right? So we are talking about first anchor. So that's the second anchor. That is the pedestal. Forget about the anchors in the back for now, because case one is all about the anchors closer to the edge, right? And then we'll think about case two, and then we'll see which case governs. Okay. So the failure surface, I'll draw that with black now. It is going to cut the edge. There will be a little bit of interference. It's going to cut the edge like this, right? Going to cut the edge like that. And in this direction, it's going to be 1.5 CA1, right? So in other words, this entire chunk of concrete, is going to come off, right? So the code says you consider though this is the surface shown in black here is the failure edge or surface. The code says you have to consider the projected area of this surface onto this face here. Okay, so if you projected that surface onto this face, that means we are talking about this entire width, which is that width, which is nothing but 24 inches, right? And we are talking about 1.5 times of CA1 in this direction. Okay, and somewhere below this is your concrete pedestal. Somewhere here is your concrete pedestal, like that, right? So case one again is about the anchors closer to the edge, and we find out the strength of those, and then we come back and calculate case two. We do the case two. Okay. So AVC. So before we go to AVC, if you go back to the code and check what we are at 17.5, we need to go to 17.5 because that is the section that talks about shear, right? 17.5 is here. We're talking about concrete breakout strength. So concrete breakout strength, we're not talking about a single anchor, so not this one. We're talking about a group of anchors when the shear is perpendicular to the edge. So, right? So we're talking about this equation here. And this equation, like I said, VB is the basic strength, breakout strength of concrete um, um, of one anchor, and then that is assuming that it is in a cracked concrete scenario, right? Then you calculate that, multiply it with a bunch of factors, and then you take AVC by the ratio AVC by AVCO, and then you calculate your group capacity. Okay, so let's copy that equation here. Let's go back there and we start writing our equations. So we're talking about VCBG. So V VCBG for the code is AVC by AVCO when that this is the area when there is no constraint, right? Then you multiply it with the CEC, oh sorry, CE, okay, EC comma V, which is eccentricity related modification factor, CED comma V, which is edge distance related modification factor. Again, this V is, all the V's are shear. CC comma N, modification factor for cracked concrete. CHV, if your embedment is um, much shallower into a member that is very thin, then you need that modification factor. You multiply with that with VB, which is your basic basic strength. Okay, so because we don't have eccentricity, the loading is not eccentric. There's no indication in the question that this is an eccentric loading, so that factor is 1. We are not in a shallow, very thin member. The depth of our pedestal was way more than um, what was needed, right? So there's no indication in the problem that this is a thin member. This is not a member like that wherein the um, anchors are being embedded. So this value is 1.0. We need to calculate VB, we need to calculate this, we need to calculate that. So let's start with CED comma V. Again, this is edge distance related modification factor, usually a function of what your CA1 and CA2 are, right? In this case, CA2 is 8.0 and your 1.5 times of CA1 is 14.25. Now, if we'll go back to the code in a moment, but then when CA2 is less than 1.5 times CA1, then CED has to be calculated as 0.7. This is all there in the code. You don't have to memorize anything. CA2 by 1.5 times CA1. So that, where is that in the code? Let's go back. So all the modification factors are here. So see, if I go down, right? So this is where you have your ED modification factor. If you see that, this is about CED comma V modification factor for edge effects. If our anchor were to be sufficiently far away from the edge, this would have been 1, but our anchor is not far away from the edge, so we need a modification factor, and that is calculated from here. Okay, so now that we are here in this section, again, this is an essential skill. When you are here in an exam, then you're working on this one, but if you think this is also useful for your problem, then you need to pick up that. You should not go back to your calculation page and then come back here. Okay, so CCV is 1.4 because we have the analysis indicates no cracking at service loads. That is in the problem description. So that's why this is 1.4. Okay. So let's go back to our problem and then fix those numbers, calculate those numbers, right? So this one here is 0.7 plus 0.3 times your CA2, which is 8.0. Again, CA2 means you have your anchors like that. Okay, shear is being applied like this. This is the edge that we are talking about, right? So from the edge along the direction of the shear force, the dimension is CA1, which is 9.5. Why is it 9.5? This is 5, that is 24. So this is 5 minus 24 by 2, which is 9.5. And CA2 is this distance here from here to here. So that is 8.0 because this is 8, 8 and 8. 3 eighths, 24. So 1.5 times of CA1, which is your 9.5, and you calculate that value, the factor will be 0.8684. Okay, so that is your psi ED. Now, so we got this one as 0.8684. Psi C comma N, we found out that this value is 1.4 because we are in an uncracked condition. Remember, VB is assumed that is calculated assuming that it is the anchor is in cracked concrete. Because we are not in that scenario, we can amplify it by a certain value, and that is 40% in this case. Okay. So we calculated what psi Cn. Now let's calculate what else is needed. Psi Cn. Now we need our VB, right? The basic breakout strength. So the basic breakout strength, it has two formula. We'll go back to the code to look at it, but then this is LE by dA. LE is the LE has a in this case it is equal to HEF, which is embedment depth. But we'll go back to the code to find this formula there. So 7 times that times of your square root of your anchor diameter, lambda A, square root of FC prime, that's a compressive strength of concrete, CA1 power 1.5, right? So this is, in this case, LE is HEF. LE is equal to HEF. We'll go into the code to find out why that is and where it is. Right? VP LE HEF. So that value there, let's go back to the code to find out that formula, and then we'll come back here. So the basic breakout strength will be before the factors, HEF. Right? So LE, HEF. So this is what I was referring to, HEF. Right? HEF is nothing but when you apply shear, HEF is the embedment depth. Right? So let's go calculate that value. So this value here, HEF is 8.0, diameter 0.75, power 0.2, square root of 0.75, lambda is 1.0, square root of FC prime 35,000 psi concrete. Then this is 9.5 power 1.5. Okay. This is one thing, but there is also an upper limit in the code saying that this value should be less than 9 lambda A into square root of FC prime, 9.5 power 1.5. I calculated this before, so that value is not governing. In this case, this value is governing because that is a lower value, and that value comes out to 15.59 kips, right? Because 9 times lambda A, because we have normal weight concrete 1.0, square root of FC prime 3500 times CA1 is 9.5 power 1.5. That will become your VP, which is 15.59. It is not this value because that is higher than the other one. Okay, so this is your basic strength of one anchor in cracked concrete, right? Um, so we still have to calculate, we did calculate A and C, right? And A and C is nothing but, one last time, A and C is, you have anchors like that. We're talking about only these two, that is case one. So the failure surface will be like this, right? Look at it in this view. Your two anchors are here. This is 1.5 CA1, and that's how the chunk of concrete that's gonna fail. The projected area onto this face, onto this face, AVC is the projected area. If you look at the definition, it is the projected area of the shear failure plane, right? So when you project it onto that area, now look at it from this view, it is cutting the entire width, right? So entire width, but how deep? 1.5 times CA1 deep, okay? So that would be, so this entire area would be your shear area, your A and C. So that is, width is 24, so 24 times depth is 1.5 times of CA1. So this will come out to 342 inch square. Okay. Now the next thing you have to calculate is AVCO, because that is what is here in this formula here, AVCO. So VCO is when there is no interference of any edge, and this for single, AVCO is not for the group but single anchor. So if you have a, let's take you have, let's say you have a big concrete pad, your anchor is somewhere here, you apply shear, then it'll the failure, I mean, let us say this is CA1, right? When you apply shear like this in this direction, the failure plane will be 1.5 CA1 this side, 1.5 CA1 this side, that is 3 CA1, right? And how deep is it? If you look at it on this view, if that is your anchor, the depth of, and this is your embedment depth. So this particular crack, or the chunk that fails, is starting, the depth of that is 1.5 times of CA1. Okay. So now again, like I said, this is the failure, this is the failure plane, that's the failure plane, but the area that we are talking about, VCO, is the projected area onto this edge, that is onto this edge. How do you calculate that? You need to look at the footing in that direction. When you look at the footing in that direction, then it will be, your anchor is here, and this this is 1.5 times of CA1. This is another 1.5 times of CA1, right? So that's your plane. How deep is that? That is 1.5 times CA1 deep. So we are talking about that area. Okay, area which is 3 CA1 wide, 1.5 CA1 deep. Okay, so that is 3 CA1 times 1.5 times of 1.5 times of CA1, which is 4.5 CA1 square, which is 4.5 times of CA1, 9.5 inches, 9.5 square. That accounts, that is roughly 406.125 inch square. So that is your AVCO. We're getting close to calculating the strength of the group. So again, VCBG is your AVC, which is 342 by AVCO 406.125. CED was 1, CED comma V was 1, right? And then you have your CEC, eccentric, there's no eccentricity, so that factor CEC comma V is 1. CED, we calculated that as 0.8684, right? Now the other one was a cracked concrete, that was 1.4 modification for cracked concrete. The other one was about H comma V, shallow depth, which is 1.0. You multiply that with the VB, which is basic strength of concrete. We found out that the second equation was governing, and that 15.59. Okay, so now you do all this, you end up with 15.961 kips. Okay, so that is phi CBG. Okay, that is the strength of the group under consideration. Okay, so wherein we were talking about this anchor, this anchor and that anchor. Yes, we do have those anchors, right? So we need to account for that. But for those anchors, you have a um, um, you need to consider the breakout of those two, correct? CVPG, this is basic breakout. Um, so this is for these two anchors, and you have this one. This is another. It's going to feel like that, right? Um, but once this fails, this will lose meaning, correct? So once these two fail like that, this will lose meaning. So the limiting shear strength uh, is just 2 times of. So for the group, it is that is the factored shear, nominal shear for the group of 4 bolts is 2 times of the capacity of these two, right? So 15.961 is for these two. That means each one is 15.961 by 2. So 15.961 by 2, 15.961 by 2, 15.961 by 2, 15.961 by 2. That is nothing but 2 times of 15.961, 15.961, which is 22.34, right? So that is your phi VN, right? Again, on last time, the capacity of these two we calculated, but once that crack forms, right? Once that surface fails, even if these things can handle more, we are not going to account for that because this has already failed. So we'll assume that um, out of the 15.961, half of it is on this bolt, half of it is on that bolt, and it's the same thing. So this value here is 15.961 by 2. This is 15.961 by 2, and the same thing here, 15.961 by 2, 15.961 by 2, right? So that is 24.34 kips. Okay, so now this is from concrete breakout, and this is again case 1. That means we are only looking at that group closer to the edge failing. So what we will do now is we'll move to case 2, correct? So that is what right, we have 2 bolts like that. What if this thing fails like that, right? So we are applying shear. That means in this case, when this crack appears, then these two go away along with this entire chunk of concrete. So their strength doesn't really matter, right? Meaning, if you look at it from this view again, so this is your pedestal, one set of anchor, other set of anchor, right? In this case, CA1 is from here to here because that is the edge we are talking about. Here is the shear force, and the dimension along the shear force is CA1, which is nothing but um, your CA1 will be this is 9.5, correct? This is 5, and this is another 9.5, right? So CA1 is 9.5 plus 5 plus 5, just 14.5. So 1.5. So this depth here of the crack is 1.5 times CA1. 1.5 times CA1 is 21.75 in this case. That's a pretty deep. It goes at the 35-degree angle. So that's the crack, right? So that is 35 degrees. So this is the chunk of concrete which will fall. When this falls, the strength of this doesn't matter. It goes along with the concrete piece, right? But then the so now let's calculate the AVC, right? AVC again. This is the, let's say this is the failure surface, correct? But AVC is the projected value of that failure surface onto this edge here, correct? So AVC is nothing but, that means if you look at it, you look at, this is the plan view, right? This is the plan view of the foundation. If you look at it from this view, your pedestal is like that. You have two. We know the depth of this thing is 21.75, which is 1.5 times CA1, which is that depth, right? And the width, again, this is cutting the entire width of the pedestal, right? So the projected cut is covering this entire width here, right? So the width is 24, the depth is, so the width is 24 times, the depth is 1.5 times of CA1. In this case, CA1 is 14.5. So that is close to 522 inch square. Okay, so that means we're talking about this area here. That is your AVC. Still there is a pedestal and then there is that foundation there. Okay, now AVCO without, this is without any edge constraint issues, and this is for a single anchor, not a group of anchors per definition, right? If you go to the code, it says that it is 4.5 times of CA1 square. How do we get 4.5? Imagine that's this vast expanse of concrete. Your anchor is here. You're applying shear like that. So that is your, that is let us say this is CA1. Okay, so let us say that is or I should draw it a little more slightly better way, which is, right, so that is your, so that's your concrete. So this is CA1, right? So 1.5 CA1, 1.5 CA1, that is 3 CA1 in that direction, right? And 1.5 times of CA1 in the other direction. 3 CA1 and 1.5 times CA1 in the other direction. So that is 3 times 3 CA1 times 1.5 times of CA1, which is nothing but 4.5 CA1 square, which is nothing but 4.5. In this case, CA1 is 14.5 square, which is roughly 946.13 inch square, right? So if there is no edge constraint issue, then for one anchor, AVCO is that much. So we know we calculated AVC, we calculated AVCO. We'll move to the next step, wherein we write down the formula for VCBG. VCBG, again, same formula, AVC, AVCO times CAD, comma V, edge distance related modification, CEC, comma V, eccentricity related modification, CCV, cracked concrete related modification, CHV, your shallow embedment related modification, times your VB. Okay, no eccentricity, that is 0, no shallow depth, that is 0, right? So now we have to calculate CED, comma V, right? So CED, comma V, like I said, is a function of CA1, comma CA2. So you calculate your CA2, which is in this case it 8 point, still 8.0, right? Because why is CA2 8.0? You have your 4 anchors like that. CA2 is this distance, which is 8.0. 8.0, the spacing is another 8.0, and this is another 8.0, making this entire thing 24, right? So that distance is again CA2, right? So 8.0, whereas 1.5 times of CA1 is 1.5 times of 14.5, which implies CA2 is less than 1.5 times of CA1. When that happens, the code says your CED, comma V value is nothing but 0.7 plus 0.3. Your CA2 by your 1.5 times of CA1, right? 0.7, 0.3, CA2 is 8.0, 1.5 times of 14.5 here. So that is close to 0.8103 C ED comma V, right? So that's your factor. Now we calculate this factor here, and that is from the code. See CV modification factor. When you have when there is no crack, you can take advantage. We already saw that in the code, right? Now the only thing left is to calculate your VB value, okay, which is basic strength. Again, VB, we have two formula. One is 7 times of LE by diameter of the anchor, or zero point 0.2 square root of the anchor diameter, lambda A modification factor for lightweight concrete, square root of FC prime compressive strength of concrete, times the CA1 power 1.5. So that is 7, 8, diameter of anchor is 0.75, 0.2, right? Square root of 0.75 times normal weight concrete. So that is 1 square root of 3500 times your 14.5 power 1.5. Why is CA 14.5? We're talking about not these anchors, but we are talking about these ones here now. That is our case 2. So when shear comes in that direction, that is the width, that is how the failure plane will be. It's cutting the entire width, right? But CA1 is along the direction of the shear, which is like this. This is CA1, okay? And that edge distance is CA2. And this one is nothing but 9.5, which is from here to here, plus your spacing, which is 5, which is 14.5. That's why CA1 being used here for case 2 is 14.5. So you compute that, and then you also compute your, but this whole thing has to be less than 9 times lambda A square root of FC prime times CA1 is times CA1 power 1.5. In this case, again, I think this will you can plug and check, but then I think this will come to 29 point. This thing here will come to 29.4, or let's see, 9 times of 1.0 times square root of 3500 times CA1 is 14.5 power 1.5. Okay, 14.5 1.5 square root of 3500 times 1 times 9. Yes, so that is 29.39 kips. Okay, so VB is 29.31 kips, because this is smaller than this entire thing here. Okay, so now once we know VB, VCBG of the entire group is nothing but the ratio of your areas there. In case 1, case 2. Okay, case 2, we need to compute the area ratio. So in case 2, our AVC, did we calculate AVC? Not yet. This was for case 2. So AVC is that much, 522, AVCO 946. So we go down here, right? So 522 by 946.13 times your factors. 1.0, this is due to eccentricity. 0.8103 edge distance, cracking, shallow depth, no shallow depth, and then your basic strength 29.31, which is this one here, right? So that will be roughly 18.4 kips. Okay, 18.4 kips. So again, this is our case 2. We're talking about these two bolts, not those. But unlike the other two, when this one cracks, these two things go away with the chunk of, if you're looking at this thing in that direction, this is the bolt, that is these two are here, these two are here, right? When this crack forms like that, with the depth of 1.5 times of CA1, then the strength of these two things are useless. So the group capacity, it cannot be multiplied with the 2. So it is just that value. But then the factored nominal is you apply that factor on this 18.4 kips. Okay. Now this factor, whenever there's a strength reduction factor, you need to see if this is in steel, the limit state that we are talking about, if it is in steel or if it is in concrete. In this case, this is concrete, and there is no supplemental reinforcement. So if you go back to that section that I showed you earlier, you'll find that your factor strength reduction factor is that much. So you multiply that with 18.4, roughly 12.8 kips. Okay, I think that is the lowest that we have seen. Okay, so 12.8 kips is the lowest yet, because if you go to your case 1, your VVN was like 22.34, right? If you go further back and you find out that your shear strength from the steel point of view is 31, so 31 is greater than 23, and that is greater than the least value here till now is 12.8. So this currently, till here at least, this governs, right? So keep that in mind, and we'll do one last check. That is the next limit state, which is concrete pry out, right? So concrete pry out, we go back to the code and we'll see where that pry out related information is. Right? If we go here, this is breakout, correct? Just to be clear, we calculate breakout from here, concrete breakout from here, but there is an upper limit. In our case, this was the equation that was governing. So we do that, but we do this and take the minimum, which is that one. Okay. But let's go to the next limit state, which is concrete pry out. I think that is after all these factors here, pry out. Okay. So concrete pry out strength, the interesting thing is the V, you have V's on the left side, which are a shear, right? Shear meaning you have anchors. Our anchors are like this in the plan view, and shear is happening like that. Whereas that is a function of how do you calculate that? It is based on the NCP. N is, like I said, N is tension, V is shear, correct? So it is based on NCP, and NCP shall be calculated the concrete breakout strength and tension for this equation. Okay, 17.4.2. You find that, and you multiply that with your KCP value, because we are in this section here. Let's pick up our KCP value. The KCP depends upon the embedment depth. Again, in our example, that was the anchor embedment depth is like 8 inches, right? 8 is the embedment depth, which is greater than 2.5. So your KCP value is 2. So the KCP in this example is 2, because your embedment depth is greater than 2.5 inches. Okay. Now, how do you find NCP? NCP, sorry, this is for single anchor, so not this equation. We have to go to that equation. NCPG, how do you times KCP? KCP is still the same. NCPG shall be from that particular equation. Okay, and if it is adhesive anchors, then this we are not here. Okay, so we don't have to worry about that. So that is 17.4.2.1, which is section 17.4, which is page 236. Okay, so let's see how do you calculate NCPG right here. Okay, so NCPG, that equation, basic strength, eccentricity related modification, edge distance related modification, is your concrete cracked or uncracked, is there supplemental reinforcement, or this were post installed. Okay, so in our case this will be, there is no eccentricity 1.0. Yes, there are edge distance related issues, so we have to calculate. Yes, there is a cracking related issue, we calculate that. So this fellow is 1.0 because ours is a cast in and not a post installed, and we'll see that we need to calculate NB. Okay, so let's go check this modification factor. So while we are here, note down that ANCO, which is now we are talking about anchor being subjected, because yes, we are talking about shear, but then like I said, the shear is a function of the the breakout strength and tension, right? When that happens, your concrete, when you pull something like that based on your embedment depth, this will be 3 times of HEF. In this case, it will be, the failure surface will be something like that, right? And the projection of that failure surface is this entire width. Because the failure surface is wider, we'll cut the entire width. Okay, so so based on this failure surface, you have to calculate your ANC, and then ANCO here is for when there are no constraint related issues. So imagine you have huge concrete and your anchor bolt is here, anchor bolt is there, there is another anchor bolt there, right? So your failure surface will be, and okay, and it is only for NCO is for again one anchor, right? So you have this, your anchor is here, and you're pulling it like this, like this. So that's your failure surface, correct? So this is 3 HEF, assuming this is HEF, right? And in the other direction, it will be 3 HEF, right? So because this area, we are talking about the area, this fellow projected, this is the failure plane, but it has to be projected onto that edge. So if you look at it from the top, if this is your entire concrete surface and here is your anchor, you're talking about an area which is 3 HEF and 3 HEF in this direction. Because there are no edge distance related issues, meaning all the edges are far away from this anchor, and that means the influence area of this, or the projected area of that failure plane of a no constraint of an anchor which has no issues with constraint is 9 HEF square. Okay, so we'll calculate that, but then let's go back to how do you calculate. So this is what I was talking about. How do you calculate your basic strengths? Correct. Basic strength. Single anchor is that, in our case we have a group of anchors, right? But NBG is for one anchor, right? So KC lambda FC prime HEF square, KC 24 for cast in, 17 for something else, but we are not in this area, we're 24 area. Our HEF is 8, so we are not between these two, so we don't have to worry about that equation which is here. We don't have to worry about this equation because our HEF is 8 and 8 is not between 11 and 25. Okay. All right. So let's transfer all this into our canvas and then see where we are at. Okay. So let's calculate the basic strength. Let's start with NB. NB Kc times lambda A times root of Fc dash HEF power 1.5, correct? Kc we found out that we are cast in, so 24, lambda A normal weight concrete 1.0, Fc prime 3500 for this problem, HEF embedment depth, right? That's the pedestal, that is a concrete. Problem statement says it is 8.0 is your HEF, effective embedment depth, which is 8.0 power 1.5. So the whole thing 32.127 kips. Now, like I said, when you pull this like that, your ANC is, when you pull something like that with HEF, ideally it should be, I mean, the failure surface, the width of the failure surface will be 3 HEF, right? So, or 1.5 HEF on one side. So what is 1.5 times HEF is embedment is 8. So 12, but then the distance from here to here was only 9.5, 9.5, 5, and 9.5, right? Because this whole thing is 24. Whereas the cone 1.5 HEF from the center line is like 12. So the cone, that means we are cutting the entire, that means this is the failure surface, and then that failure surface will go like that, and this fellow's failure surface will be like this, right? And he is going to cut somewhere here because that will be 1.5 HEF from this side, right? So in short, the compound failure surface will be like this, but then ANC is not about that area. ANC is the projected area of this onto the edge, right? So that is the edge, project it. That means it is cutting the, that means in plan view, you're talking about a 24, um, 24 by 24, right? Because you're talking about this entire width, and same thing in the other direction. So 24 by 24 is your inch square. That means 576 inch square is your ANC. Okay. Now ANC naught, NC with no constraints, NCO, 9 times of HEF square. That's what we saw. 9 times of 1.5. Sorry, 9 times of HEF is 8.0 square, which is also 576. Okay, that's about this one. Now, after we calculate our, okay, after we calculate our, so let's say we calculate N, NCBG is just, is NCBG, what is NCBG? ANC no constraint, CED in tension, I think EC, right? Bunch of modification vectors, right? So let's go back to the code. To memorize, I did not memorize that equation here in CBG. Okay, CED, EC, ED, C, CPN. ED, C, CPN. Okay, so that one here is your ED, EC, C times of your basic strength, which is that fellow there, right? So ANC naught equal to 1.0 because both are 576 inch square. So 1.0 times of 0.9, right, times 1.25. If you look at EC, sorry, this fellow here for uh, for tension, that is 1 point in the code, that is 1.25, not 1.4. 1.4 was for shear, right? You multiply that with your CPN, no issue there. We're not post installed, we're cast in, right? Then the basic strength 32.127. So that results in 36.14 kips, right? This is your NCBG, okay? But your what we are worried about is pry out of concrete. That is KCP times of NCBG. And KCP, because our embedment depth is greater than 2.5 inches, the KCP value was 2. 2 times of 36.16, 72.28 kips. Okay. So 72.28 kips, that is the nominal. What is the factored shear nominal? Factored nominal is your strength reduction factor, also in this case is 0.7 times of 72.28, 50.59. So that is 50.59 kips. Okay. So this does not govern. This will not govern because the least value was in this in the case 2 version, wherein when this particular surface fails, then these two become helpless because they get carried along with that volume of concrete. They move out with that volume of concrete. You're talking about just this one, and that strength is only, so if you apply 12.8 kips, then this crack will start to happen, right? Or the nominal strength of this mechanism is like 12.8 kips, right? But that governs because that is the least value. We have other value. We calculated the other values, and those were, for example, case 1, this was 22.36 kips. Case there was another case wherein we're looking at shear strength of the anchors, and that was 31.2 kips, right? So in short, the one that governs is this value here, which is case 2. Okay, so the problem statement said the pedestal with that grout, and then it is a column. Okay, let's do it here. Here is a pedestal, that's a grout, that is the standoff, and there is a base plate, and here is your column. There are two anchors, and the shear given was VU was 30, right? So 30 kips is the applied, whereas the resistance is only way greater than the resistance is only 12.8. So we need to strengthen this connection. So failed, right? Because applied load is 30, the strength is only 12.8 kips. Okay. So that's about this one. Like I said, what we did, just to summarize, is to check the, let's go back to section 17.3, which is 236, about that. That is where all the failure modes were defined. The problem is about finding the shear capacity. So we are looking at that one, steel strength in shear, and that was a much higher value. Concrete breakout strength of anchor in shear, and then pry out strength in shear. So pry out strength was also a decent amount. The least one was this. This was 12.8 kips in our example, but the load coming was 30. So that's a failure. Okay. The main important thing is to understand that we need to consider two load cases, correct? Two cases, which is you have your pedestal like that, plan view. There are 4 bolts, shear coming this direction, right? Case one is when this one fails, the bolts close to the edge fail. Okay, what is your phi vn value that will cause this failure? Okay. Then case two is you have to look at these bolts, those bolts, and figure out um, the failure area. Why will this phi vn, let's call it phi vn2, phi vn1, why will phi vn2 be different from vn1? That is because in phi vn2 case the ca1 is that much, whereas in this case, because you're talking about these bolts, your ca1 is that much. Okay. And the same thing, I mean, when you look at it from this view, you have your pedestal, right? 24, this is 24. You have your two anchor bolts, but that um, distance where the crack will form is 1.5 times of the bigger CA1. That means this distance is huge. That means that's how the failure thing looks, right? So that's how the failure thing looks. So that means this concrete chunk will go away. When this goes away, most important thing is to realize that the strength of these two anchors is useless because they are anyway going away. That's why we did not multiply the VC BG value with a factor of 2, unlike in case 1. In case 1, when this fails, just before it fails, this anchor is active, that anchor is active, this anchor is resisting the load, that anchor is resisting the load. Okay, so let's say this cracks will start forming up at let us say 15 kips, right? 14.9 kips, this is active, no cracks formed, so this is sharing the load 14.9 by 2, 14.9 by 2, 14.9 by 2. Sorry, 14 point. Let's say this entire this 14.9 is the entire shear acting in this direction. So that by 4, that by 4, that by 4, that by 4. Okay. So it's important to, the most important thing is to visualize the areas, and then visualize the failure planes, and then visualize how the projected areas are calculated, and then how do you calculate your group capacity. Phi, when they say phi VCBG, it's not about the four anchors, right? You need to clearly calculate, understand if you are in case 1 or case 2, and calculate your phi VCBG accordingly. Okay. All right. If you have any questions, let me know. Otherwise, it's a simple problem, but there's a lot to visualize and pick up. Right. Thank you.